Okay, I think we can get started here with the next talk. So we will now have Lauren Williams talking about the TASEP on a ring, Schubert polynomials, and is that evil avoiding permutations?
Yes.
Yeah, take it away.
Yes, so thank you so much. Thank you to all of the organizers, Maria, Laura, Oliver, and Liam for organizing this nice conference and inviting me to speak. So I'm going to speak today about joint work with Donghyun Kim, who's a finishing PhD student at UC Berkeley. He'll be applying for postdocs in the fall, so please keep an eye out for his application. I have to say I changed the topic of my talk a few days ago. If you were hoping to hear about the hypersimplex and amplitude-hedron and Eulerian numbers, then I would encourage you to go to the poster of Matteo Parisi, who's one of my co-authors, along with Melissa Sherman Bennett on that work. Okay, so here's the outline of my talk. I'm going to say a bit about a Markov process, the exclusion process on a ring. I have a little picture of it here. We have particles on a circle of different weights, and they can, consecutive ones can interchange places. And then I'm going to tell you a little bit about its stationary distribution and connections to Schubert polynomials. And then I will explain some results for this new class of permutations that we call evil avoiding permutations. So just to give some very general background, the asymmetric simple exclusion process, or ASEP, is a Markov chain introduced by biologists in 1968 as a model for translation and protein synthesis. And it was independently introduced by a mathematician, Spitzer, almost at the same time. And in this model, one has particles hopping on a one-dimensional lattice. There's at most one particle per site, and particles could have different weights, which are indicated by the numbers in the balls, and these weights can affect their hopping rates. And the lattice could be a line with open boundaries, or a ring. Okay, just to say, it's a very well studied model, this and various versions of it, and this is a very incomplete list of names of people who have worked on the ASEP. Now, in this talk, I'm only concerned about the exclusion process on a ring, and even when you go to the ring, there's at least two versions of it, and a version that we might call the usual multi-species exclusion process has particles of different weights around the circle, and then they swap places either at a rate proportional to 1 or proportional to t, depending on whether the heavier particle is clockwise of the smaller or is counterclockwise of the smaller. And this model is extremely interesting. And one of the reasons that I find it interesting is that it is connected to Macdonald polynomials. And this was first realized by Cantini, De Geer, and Wheeler a few years ago. And then in some joint work with Sylvie Cortiel and Olia Mandelstam, we were inspired by their work and built on it to use this connection to give new formulas for Macdonald polynomials. Now, the other version of the exclusion process on a ring is what we might call the inhomogeneous totally asymmetric exclusion process, or TASEP for short. And in this model, the hopping rate is going to be more refined. So if I have two particles adjacent to each other, then the hopping rate is going to be x4. So in this example, x4 minus y6. 4 is the weight of the smaller particle, 6 is the weight of the larger particle. But I'm only going to allow adjacent particles to swap places if the bigger one is clockwise of the smaller. And in this version of the exclusion process, we see connections to Schubert polynomials. And this was first noticed in a 4-page paper that Lam and I wrote in Experimental Mathematics. This is a paper which has only conjectures and essentially no theorems. Cantini then did some work in which he started to make a connection to Schubert polynomials and showed some special states that were proportional to Schubert polynomials, or probabilities were proportional to Schubert polynomials. And then we have a refinement of this and more connections in the work that I'm speaking about today. Okay, so now let me explain in a little more detail what's the inhomogeneous TASEP on a ring. So we are going to fix a lattice of n sites on a ring. And this is going to be, my sites will be filled with particles with weights 1, 2, up through n. So I have n distinct sites and my particles will have distinct weights. I could in fact allow weights to repeat. I could allow several particles of the same weight, but to make the connection to Schubert polynomials most clear, I want to restrict to this version where the particles have distinct weights. So now this is going to be a Markov chain, and it has exactly n factorial states. And the way that I identify a state with my permutation is I'm going to choose some fixed but arbitrary place along the circle. I'll cut it open, and by cutting open the circle, I will identify states with permutations. So in this example that I've shown here, after my cut, I see the number 2, then 7, then 8, 3, 5, 1, 4, 6. So I would identify this state that I've shown with this permutation. And as I mentioned, my transitions involve swapping adjacent particles. And if I have two adjacent particles, I and j, where I is smaller than j, then I can transition to the related state where I just switch j and I. And this happens with rate xi minus yj. And otherwise, if I is greater than j, then this transition does not happen. It happens with probability 0. So by the way, please feel free to interrupt if there's questions. I'm not always good at monitoring the chat, so just unmute yourself if you need to ask a question. Okay, so now what are the steady state probabilities? So steady state probabilities, these are the probabilities that one gets in the distribution you obtain as you let time goes to infinity. And for W, a permutation in Sn, which I'm thinking of as a state, we let psi sub W be the unnormalized steady state probability of being in state W. So what do I mean by unnormalized? So if we look at our probability distribution, the steady state probability distribution, these are going to be, it'll consist of rational functions in the x's and the y's. Let's choose a common denominator, and then we'll just clear denominators. And what I have left is what we call the unnormalized steady state probability. These are just going to be polynomials in the x's and y's. And just to make a basic remark here, of course, we have this circular symmetry in the model. And that is reflected in the steady state probabilities. So for example, the steady state probability of the state 3, 1, 2, 4, that's if I'm talking about a lattice of just 4 sites, is the probability of the state 1, 2, 4, 3 is the same as the probability of the state 2, 4, 3, 1 is the same as the probability of state 4, 3, 1, 2. And so we can restrict attention, or without loss of generality, we can always consider, when we're looking at probabilities, we can always just be looking at permutations in Sn with W sub 1, the first letter, equal to 1. Okay, so let's look at a small example. This is the case n is 4. And here I've drawn only the states, starting with a 1. And I'm showing you some data. And to make it a little cleaner, I just set all the y sub i's equal to 0. And then what we see here on the right-hand side is we have monomials. And we also have these polynomials, which are Schubert polynomials associated to permutations. So yeah, so my math frac S sub w is the Schubert polynomial associated to W. And let me just remind everyone of what Schubert polynomials are. So we have our divided difference operators, which act on polynomials P. And del IP is obtained by taking the polynomial P, subtracting off the result of exchanging xi and xi plus 1 in P, and then dividing by xi minus xi plus 1. And then if we have a reduced expression for a permutation W, and if we concatenate the divided difference operators corresponding to that reduced expression, this operator depends only on W, and so we can denote it by del W. And now if x1 through xn and y1 through yn are two sets of variables, we can let delta of xy be this product of linear polynomials and the x's and y's. And then to every permutation W, we can associate the double Schubert polynomial obtained by starting from this factor and applying divided difference operators corresponding to W inverse W naught, where W naught is the longest permutation. So this is how we define double Schubert polynomials, and ordinary Schubert polynomials are obtained by letting the y sub i's equal to 0. Schubert polynomials generalize Schur polynomials when W is a Grassmannian permutation. So in fact, both Macdonald and Schubert polynomials generalize Schur polynomials. And the geometric significance of Schubert polynomials is that they represent cohomology classes of Schubert varieties in the cohomology ring of the complete flag variety. And there's also a geometric interpretation of double Schubert polynomials as well. And there's been a wealth of combinatorial formulas for Schubert polynomials. So this is just a very incomplete list here. Okay, so now let's go back to our data about the steady state probabilities. And this is now the case where n is equal to 5. So first, let me just explain some of the notation that I have here. So x to the 520 is shorthand for x1 to the 5, x2 squared, x3 to the 0. And as you can see in this table, most of these unnormalized steady state probabilities are equal to some kind of monomial in the x's times product of Schubert's. And okay, I should say again in my table, I've set y sub i's equal to 0 just to make it more readable. But there's versions of this where the y's are non-zero. Let's see, there are only 4 places, there's only 4 steady state probabilities where I have this non-trivial sum of terms. So this state, this state, this state, and this state. And I'll point out that even in those 4 cases, we see something nice, which is that we see a positive sum of Schubert polynomials. So let me just write down one of the questions you might ask here. So when is psi sub w equal to a product of Schubert polynomials. And really, I should say a monomial in x's times product of Schubert polynomials. So we did a lot of computations here, and we started to see that pattern avoidance seems to play a role.
Lauren?
Yeah?
Each of your monomials is itself a Schubert polynomial.
Yes. Sure. Yes. That's a good point. Each of the monomials is also a Schubert polynomial. We were focusing, I guess, on the non-trivial terms. So we were factoring out the monomials as well. As much as, yeah, we were factoring out the highest monomial we could. But yes, you're absolutely right that each of the monomials is a Schubert polynomial as well. Any other questions before I go on?
There's a question in the chat.
Oh, yes. Alex Young says the bad cases also use Schubert's and SN for n greater than 5. Yes, this was something that was a little bit disappointing to us, right? We're working with steady state probabilities for n equals 5, but we had to go up to Schubert's with as many as 7 letters here in order to express it. Yes, but they don't have descents after 5. Yes, so there's some good things and there's some bad things about this picture. Okay, but so now let me go to this question. When is it that these steady state probabilities look like they are proportional to products of Schubert polynomials? And I claim this has to do with pattern avoidance. So let me review the definition of pattern avoidance just very quickly, since I know most of you are familiar with it. So we say a permutation W avoids the pattern 2, 4, 1, 3. So I'm defining by example. If there are not 4 positions, I, j, k, l, such that in my permutation, Wi, Wj, Wk, Wl are in the relative order 2, 4, 1, 3. For example, this permutation contains the pattern 2, 4, 1, 3 because these red letters have the same relative order as 2, 4, 1, 3. Okay, so now let me get to this definition of evil avoiding. So we will say that a permutation W is evil avoiding if it avoids the patterns 2, 4, 1, 3. I'm going to identify 2, 4, 1, 3 with the word evil by associating 1 to I, 2 to E, 4 to V, and 3 to L. And also the patterns coming from these anagrams of evil. So we have vile, and by my association of letters to numbers, this should be 4132, and also veil, this is 4213, and also leave, which I realize is a little bit of a stretch for an anagram, but it is a name in some Scandinavian languages. So, so you're evil avoiding if you avoid evil, vile, veil, and leave. Okay, so so here's a vague statement of the theorem. If W is an evil avoiding permutation representing a state of the TASEP and without loss of generality W sub 1 equals 1, then the unnormalized probability psi sub W is proportional to a product of K double Schubert polynomials, where K is the number of descents of W inverse. Yes, there was a question about the word live, but the word live is not evil enough, so that was excluded from our list of anagrams. Okay, so now back to the data. Evil is 2413, vile is 4132. So these are our 4 bad patterns, and you'll see that they are precisely contained in the 4 states where the steady state probabilities were proportional to non-trivial sums of Schubert's. And you can also see, if you start looking at how many Schubert polynomials appear after I've factored out the largest monomial, then this number is equal to the number of descents of the inverse. So this permutation here, let me actually use another color. This permutation here, its inverse has 3 descents, which is corresponding to these 3 Schubert polynomials here. And if you look at the inverse of either of these 2 permutations here, the inverse has 2 descents. And that's related to the fact that we have 2 Schubert polynomials over here after factoring out that monomial. So this connection is another reason that we want to kind of factor out that highest monomial to make the connection with descents a little more clear. Okay, so just to say a few words about the combinatorics of evil avoiding permutations. The enumeration is straightforward. The number of evil avoiding permutations is given by this formula, and it appears in Sloan sequence A006012. And evil avoiding permutations do not appear in Sloan, although I hope they will in the coming weeks. I think Donghyun Kim is going to add them. But this number of evil avoiding permutations agrees with the numbers of rectangular permutations, which avoid a different set of patterns, and also several other interpretations. And so it would be interesting to find any kind of bijective proof of this, sort of any bijection between evil avoiding permutations and one of these other objects that appears in Sloan. We haven't really looked into it, but it wasn't, at least the sort of 15 minutes that we did look at it were not sufficient to find a bijection between these permutations. Okay, so I want to state our theorem in a more precise way now, and so that is on this slide. So let's take a state of the TASEP coming from an evil avoiding permutation, and let's say the number of descents of the inverse is k. Then what we do to make the connection with Schubert polynomials precise is we associate 2w k partitions, lambda 1 through lambda k, and then we define another permutation mu, which is this vector minus the sum of all of these other k partitions. And then the steady state probability. Oh, and I should say, I'm stating this theorem in the case where y sub i's is 0, but there's a version where the y sub i's are non-zero. So then the steady state probability of psi w is this monomial factor x mu comes from here, times the product of the flagged Schur polynomials of shape lambda I, where entries in row j are bounded above by this number. And flagged Schur polynomials are Schubert polynomials associated to vexillary permutations. So this is the precise statement of the result once I have told you what these k partitions are. And to get these partitions, you take the lemma code of the inverse. You set A0 equal to 0, and you let the A1 through AK be the descent positions of the lemma code. And then lambda I is this kind of rectangular partition minus a vector formed out of a portion of the lemma code. So yeah, so it's totally explicit, although a little bit complicated. So if W is 1, 4, 2, 5, 3, then the lemma code of W inverse is 0, 1, 2, 0, 0. A0 is 0. A1 is 3. That's the position of our unique descent here. And then the partition that we associate to W is this kind of rectangular vector minus a portion of the lemma code, which in this case is this part, and then we get 2, 1, 0 out of it. Okay, so a little complicated, but totally explicit. And this is a little table here showing how we can get from our evil avoiding permutations to tuples of vectors. These are the sequences of partitions, lambda 1 up through lambda k. And so in any of these rows, if you look at the sequence of partitions here, together with the monomial vector here, the sum of these vectors is constant. And so throughout this table, that sum is going to be 6, 3, 1. Okay, so this again at the top is the theorem connecting steady state probabilities to Schubert polynomials. And and I should say, we have this theorem also in the case where y sub i's are non-zero. If you're in the case where y sub i's is 0, the first thing you might try to use to prove this theorem is a combinatorial formula for the stationary distribution in terms of multi-line Qs. This formula was first conjectured by Iyer and Linnesen and proved by Arita and Malik. And in this case, and when k is 1, we can use it to prove the theorem bijectively. But it's not so easy to use multi-line Qs to show that steady state probabilities look like products of multiple Schubert polynomials. So for that, we need a more general technique. So to prove the theorem when the y, and also, if the y sub i's are not 0, there's no multi-line Q formula. So the tool that we use here is a theorem of Cantini, which describes steady state probabilities sort of recursively after adding some auxiliary parameters z1 through z sub n into the picture. So this is the statement of his result. You start with this sort of complicated so instead of working just with steady state probabilities, we're going to work with these sort of z-enriched steady state probabilities.
Excuse me, Lauren, 2 minutes left.
Okay, thanks. So you sort of associate a quantity to this canonical state, and then there's a kind of isobaric divided difference operator that you can use to get expressions for other steady state probabilities, enriched steady state probabilities, and then leading coefficients of these objects are the actual steady state probabilities you're interested in. So we need to show that if W is evil avoiding, then the leading coefficients of these objects look like products of Schubert's. Okay, so so I just end with a conjecture that if W is not evil avoiding, then we can write psi sub W as a monomial times a positive sum of Schubert polynomials. And you can make this sort of conjecture by, you have to be a little careful, but you can make a version of this conjecture also with double Schubert polynomials. When you work with the y sub I as non-zero, then these monomials here get replaced by products of sort of linear factors and x's and y's, you know, things like xi minus yj. And a question is there a geometric interpretation to the psi sub W, since we are seeing these unnormalized steady state probabilities expressed, at least in small examples, as positive sums of Schubert polynomials. So I will stop there. We have an extended abstract on the AlCoVE containing all these statements, and the longer version with proofs should hopefully come in the next month or so. So thank you very much.
Thank you, Lauren. Let's give our speaker a round of applause. There's a number of questions in the chat that were sort of floating in here. So Bridget asked, what is the OEIS reference? I think it was posted there.
Oh, yes.
Then Alan Knutson, I think, has the next question. Alan, do you want to unmute to ask it?
Well, I think it was answered, but about to what extent Cantini's result implied Schubert positivity.
Yeah.
Oh, yes. So his result didn't imply Schubert positivity, but he showed, so for each of the n factorial, so if you fix n, those n factorial states, and among those n factorial, he found n special states where steady state probabilities were proportional to single Schubert polynomials. So he was able to use his results to identify some probabilities as looking like Schubert's, but nothing about products of several. Or sorry, maybe Donghyun can correct me if I make a mistake. But anyway, so he sort of identified 1 out of n states, a proportion 1 out of n, as being looking like Schubert polynomials.
So I also wrote a question in the chat so that I remember it. What is this theorem at all if and only if? Like if you have one that's not evil avoiding, do you know that it can't be written as a product of Schubert polynomials?
Yeah, that's a great question. We think it's an if and only if, but we only prove it in one direction.
Okay.
Yeah, I wouldn't really know how to approach in the other direction since we don't really understand the others very well yet.
Cool. Actually, I had one more little question. Just this evil avoiding, you said it was in bijection. Oh yeah, the bijective proof thing here. So is this a new interpretation of this sequence that was already on OEIS?
Yes, as far as we know, evil avoiding permutations have not been considered before. But if anybody is aware of study of them, we'd be very interested to know.
There's one more question that just came in the chat here. The flagged Schur decomposition, Benjamin Young says, the flagged Schur decomposition is pretty nice. Is there any hope something similar can be done in the ASEP?
Ben, can you clarify which version of ASEP you mean, since there's so many floating around? Do you mean the same version, but now you allow particles hopping in the other direction?
I'm not educated enough to be any more specific at all, but you've got this big story of a different class of polynomials that are characterizing steady state probabilities in various classes of ASEP involving McDonald polynomials and so forth. Like, I don't know of a push out of McDonald polynomials and flagged Schur polynomials. So I don't even know, like I say, it's a very naive question.
So I guess I could say a tiny bit about what happens in this version. So in this version, In this version, if you look at the partition function for the whole model, then the partition function is precisely a specialization of a Macdonald polynomial where you set all the xi's and the q equal to 1. And what you can, if you look at individual steady state probabilities, then what you see is specializations of certain permuted basement Macdonald polynomials.
Right. Yeah. The idea would be to sort of undo some of the specialization.
Oh, yes. So on this side, we can undo the specialization in a sense. So okay. Interestingly, multi-line Qs allow to give steady state probabilities in both versions of the model, but the parameters that you associate to them are just different. What we did with Korteel and Mandelstam was to figure out how to take the formulas for steady state probabilities in this model in terms of multi-line Qs and put back the x's and the y, just the x's and the q into the multi-line Qs to get these generating functions in terms of multi-line Qs, which are precisely these permuted basement Macdonald polynomials. But it's not clear, and it's probably not possible to put x's and y's and q into this probabilistic model, but you can do it into the combinatorial objects used to describe steady state probabilities.
Interesting. So it's totally different.
Yeah. Well, there's a lot of parallels, but there's also a lot of differences.
Thank you.
Okay, great. I think in the interest of time, we'll cut the questions here. So thank you again, Lauren, for a fantastic talk.